Okay, so the final t-test we want to look at is a two-sample t-test assuming unequal variance. So if you go to your data analysis section in Excel, this would be now this test here, a two-sample assuming unequal variance. So let's cancel. So let's take a look at the data. So we have again two groups. We have one group which is maybe considered rich and the other one is poor. And we have 25 rich and 16 poor households, and they provided information on their monthly expenditures on vegetables. So now the question is, conduct a two-sample t-test on the following two-tailed hypothesis, and again at an alpha of 0.05. So conceptually, again, there's really nothing new other than, except for the fact that this time the standard error that Excel, that you have to use and which Excel uses, looks like this, and specifically the degrees of freedom formula looks a little bit complicated. But we will derive it now step by step. So first thing we do is we copy our data into Excel. So here it is, and maybe we can maybe a little bit fit better too. Oh, that was too much. Okay, that's good enough. And now we calculate first the mean for each group. So average. Okay, so the rich spent 155 on vegetables and the poor 140. So it looks like that the rich spent more on vegetable. Now let's take a look at the variance. So the rich have a variance of 689.25 and the poor of only 246. So now that suggests that, you know, the variance is indeed different, but we still can do an F-test, which I introduced in the previous video. And again, we will talk more about the F-test later. But the F-test, where the null hypothesis is the variances are equal, and the alternative is no, they are not equal. So we use equals F.test, and then we can highlight the data array for the rich, and then we compare that to the data array of the poor. And then we get a p-value of 4%. So that means that if in those two samples, or in those two populations from which we took the samples, there would be really no difference in the variance, then there's only a 4.3% probability that we can draw two samples that will generate that huge difference in variance. And because, let's say, our alpha is 5%, we would, of course, reject the null that they have equal variance, but we could have made a type 1 error, but that is only 4.3%. And we are willing to take that risk. So we reject that the rich and the poor have the same variance in their expenditures. So now, as always, let's just illustrate again our test. So we assume a sampling distribution, and we hypothesize the null, that there is no difference. So our H0 difference of rich minus poor, so we hypothesize rich minus poor is equal to 0. And we need again the standard error. But in this case, the standard error is again a new formula. And let's calculate it later. But we have gotten our sample where the difference between rich minus poor is actually 15. So the question is, how many standard errors is that away? And so the formula for a two-sample t-test assuming unequal variance is actually a little bit easier than before when we have equal variance, because we don't need a pooled regression, I mean a pooled variance. So the formula is square root, and then we take the variance of the rich divided by the number of rich, n1, 25, plus the variance of the poor divided by 16, the n of the poor. Okay, so now we get a standard error of 6.556, 6.556, 6.556. So now we can calculate our test statistic, and still let me try to create a little bit more space here. So that's not that easy. Okay, so the test statistic, I call it test T, is now how many standard errors is a 15 away from a hypothetical mean of 0, so equals 15 divided by the standard error. Okay, so now we know that our test statistic is 2.288. So our scenario is, so here we had expenditures, and now we converted it into a T. And our expenditures of 15, well, that corresponds to a T-score of a test statistic of 2.288. 2.288. And that is our test statistic. Well, what we need to know is what is the critical T. And in order to know the critical T, what we need to do is we need to find the degrees of freedom. And you see the degrees of freedom, that's a really not so nice formula. And let me create a little bit more space here, and I'm trying to, okay, so at the 5% level we need to calculate the degree, we need to first calculate the degrees of freedom. And you see this is the formula here, which looks a little bit complicated, but what we always seem to use is the variance of each group divided by n1. So let's create maybe a term for this, and I call that S squared divided by the n. And then I'll superscript the 2. So we go to full superscript. Okay, so that is equal to Okay, the variance of the first group divided by N1, and for the first group that's 25. So we get 27.57. For the next group, it is the variance of 246.667 divided by 16. Okay. And okay. So now the degrees of freedom consists of a numerator and a denominator. Let me just do the numerator first. So the numerator of the degrees of formula is equal to S1 squared over N1 plus the variance of group 2 divided by the sample size of 2 squared. So open parentheses. So we do the 27.57 plus the 15.42. Put that into parentheses, and then we raise it by 2. Okay. So now in the numerator we have like 1847. And now the denominator. Okay, so in the denominator we have S1 squared over N1, but we have to square it again. So that is equal to the S squared over N, but squared. It's really complicated. And then divided by N1 minus 1, so the degrees of freedom, which for the rich is 24, plus the 15.42, which is S squared for the second group over the sample size of 16, but squared, and also divided by the degrees of freedom in that group, which is 15. Okay, so now we get 47. And now we can calculate the degrees of freedom, df, which is the numerator divided by the denominator, and we get 38.89. Okay, so then we have to round that up to 39. So we have 39 degrees of freedom. So you round up that number. Okay, so now I can. So I know that, so I applied that formula, and now we can determine the critical T. So I put that here now. And I put it underneath. So the T critical Okay, so we know 39 degrees of freedom, and we have an alpha of 5%. So we need to find the critical T equals absolute, then in parentheses T.inf, open parentheses 0.025, and 39 degrees of freedom, close parentheses twice. So now our critical T is 2.023. So we have to the left of negative 2.023, we have 2.5%, and to the right. So that means if we draw that into our T distribution, so this purple line, we have 2.023, and to the left of negative 2.023. We have here in each of those corners or pockets we have 2.5% probability, and we can see that our test statistic of 2.288 clearly falls into the rejection zone, because this is the rejection zone and this is the rejection zone. So at this point we conclude that we reject the null in a two-tailed test. Reject null. So that's our conclusion or decision. Reject H0. That's the decision. But we could make, of course we could have made a type 1 error. We could have now rejected the null, even though it is true. So that means in order to determine what's the probability that we made a type 1 error, we now look at the area to the right of our test statistic of 2.288, which is this area here, which is supposed to be the yellow area here. So that yellow area, and then again we have to multiply it times 2, because the error could also have occurred to the left of negative 2.288. So I don't have to draw it, but it could have happened the same on the other side. In a two-tailed test you need to multiply that times 2. So now the p-value is equal to, okay, so now we use the formula t.dist, and now we enter the negative value of our test statistic, which is the 2.288, because the area to the right of 2.288 is the same as the area to the left of negative 2.288. Degrees of freedom 39, and we want it cumulatively yes, which is a 1, and then don't forget to multiply times 2. And what we should see at this point is clearly, before I press enter, we should definitely get a value which is less than 5%. Well, it is 2.7%. So there's a 2.8% probability that we rejected the null, even though it is true. That's a very small probability that we got such an awkward sample, which makes us feel more comfortable to think that there is a difference between the rich and the poor in their expenditure behavior. Okay, so again, conceptually it's always the same, but when it comes to a two-sample t-test, assuming unequal variance, Excel will produce results that you now can also replicate, and you know where the formulas come from. So let's actually apply quickly Excel and go to data analysis, and we do a two-sample assuming unequal variances. Okay, and again our data has labels. So variable 1 range, I use the poor. For variable 2 I use the rich. You can do it the other way around. The only difference is that in this case the test statistic will be positive, in the other case it will be negative, because Excel subtracts from the variable 1 range, it subtracts the variable 2 range. So, and then the output range may be next to our calculations, maybe here, and then we just say again the mean difference is 0, but even if you didn't enter anything, Excel will default it to 0. Okay, so now we should see some results. And let's maybe increase the font size, fit to content, and so okay, so now what can we see? Our test statistic, well, it's actually negative 2.288. So, yeah, because I subtracted from the poor the rich. Okay, so if you want to see what the order of that does, now we have negative 2.288, and you see the first range is C. If I had flipped that, and the first range is the rich, and the second range is now the poor, which I actually wanted to do, then this will, the t-test will flip to 2.288. Yeah, so override it, and you see it just overrode it. And okay, let's make it a little bit bigger. So, okay, so now what can we see? Maybe okay. So, okay, we see a difference of 15. The degrees of freedom here, that's important, the 39. That's what we calculated here tediously too. So that is equal to this. Then we did a two-tail test. So our probability of having made a type 1 error, which is here the probability level, is 2.8. So that is the same as our p-value that we calculated of 2.8%. The critical value for a two-tail test is the 2.023, which is the same that we got. And we don't have to worry about a one-tail test because we didn't do a one-tail test. And our test statistic, which is the 2.228, is also the same. And again, Excel didn't report the standard error, but now you know what Excel does, because you have to look at the formula here. So this is the standard error, and the degrees of freedom is this formula. And well, yeah, now you know how to calculate that. Okay, so let's just stop here. And actually, let me quickly show you the slides. So I calculated again everything. I just summarized the main results, like the standard error, 6.556. The variance, here I also showed you an F-test, which is not in the slides, but we will talk later about an F-test. And again, we reject the null at an alpha of 5% with a type 1 error probability of 0.03, or more specifically 2.8%, but if you round it to two digits, it's 0.03. Okay, let's stop here, and then let's review some of those concepts again in a couple of problem sets. So I'll see you later.